We're starting with today's work by taking a look back at the idea of acceleration, something we did a couple days ago, seeing how well you remember that part. So check your notes if you need to, and please use that to figure out what's the acceleration after 2 seconds based on this equation. And what I'm hoping that you're finding in your notes is the statement that in order to find the acceleration function, a of t, that is the same thing as doing the second derivative of the position function, or in this case that means s double prime of t. So in order to find that acceleration, you should be finding the second derivative of our function. And so you have to find the first derivative, which is what we're looking at there, and then find the second derivative based on that. And so we find that the second derivative equals 12t minus 10. Well, that's the acceleration function then. So the acceleration equals 12t minus 10. In this particular problem, I'm looking for a of 2, because we want to know what's the acceleration after 2 seconds. And so I end up finding that the acceleration after 2 seconds is 14. Now we got to talk units though. So for units here, notice it's centimeters in this particular case, so it's centimeters per, and then time here is measured in seconds. And so it's centimeters per second squared, per square seconds. That's because what it's really meaning is it's meaning 14 centimeters per second, because this is increasing in speed by 14 centimeters per second every second. It's just when we see per second, we represent it more shorthand as per second squared. All right, we're going to be practicing finding some derivatives using those rules we learned this week as well. So please find the derivative of this function now on your own paper. And I hope that as you first look at this problem, you notice that since it's a fraction that can't be simplified at all, you're going to need to be using quotient rule here. So you should be plugging in the quotient rule as you go. And when you plug in the quotient rule, this is what you should be looking at. Now, one thing leaps out to me as I'm looking at this. I'm noticing that on the top here, I got lots of e to the x's. I have so many of them, I'm betting that I'll be able to do some simplifying up top. So let's actually try to simplify the top here and see if it's actually going to lead us to something good. So we still have f of x equals, and so first up I'm going to distribute the e to the x into both the 1 and the e to the x. Of course that gives me e to the x minus, and then e to the x times e to the x. That's e to the x squared. What does e to the x squared equal? Well, remember when we have a power to a power like this, we multiply those two exponents, so that's the same thing as e to the 2x. Okay, then minus, and now I multiply the e to the x by the negative e to the x. That's going to give me a negative, so it's minus a negative, so plus another e to the 2x there. Yeah, it's still all over the same thing. I didn't change the bottom at all. I can multiply that out if it turns out that that's going to be useful to me later. And the nice part about doing that on the top there is that we see there actually is something we can simplify. That negative e to the 2x plus e to the 2x, they cancel each other out, and the whole top just ends up being e to the x. And then the bottom, I'm just leaving it as 1 minus e to the x squared. If I multiply that out, am I going to be able to cancel out e to the x on the top there? No. That 1 is going to keep us from being able to do it, because it will never have an e to the x in that term. So I'm going to go ahead and just leave it like that. Now, I strictly speaking didn't have to simplify at this point. This is fine as a final answer. But more and more, simplifying and reducing is going to become a bigger deal and a bigger part of our process, because it's actually going to make your life easier as we go into second derivatives especially. And so just looking for some of those things where it's like, the fact there's so many e to the x's is a sign to me that I probably can simplify, and then going down that road is going to help you get a little bit of practice in that. Before we actually saw a problem kind of like this one. In fact, it was the same table, but it was a situation where we were told that r to the x equaled f times g of x. In this case, we're told that r of x is f over g of x. So, of course, seeing that setup right there, which rule am I going to need to use if I'm going to be dealing with the derivative? Quotient rule. Yeah, because we're dividing. That fraction tells me I'm dividing. So I'm going to have to use quotient rule for this. Well, conveniently enough, we are starting with f and g. So let's write out our quotient rule in terms of f and g. And so this is what we're looking at when we actually get the quotient rule out for this one. And in this particular problem now, we're told that we want to figure out what r prime of 1 is. So using the quotient rule and the table, the relevant portions of the table, please figure out what is r prime of 1. All right, so what I don't need to worry about is these grayed out rows, because I'm only looking to see what's going on when x is 1 here. So first up, I need g of 1. We can look in our table and see that is 2. Then we need f prime of 1. F prime of 1, we can look in our table, see that is 3, minus f of 1, which is 0, times g prime of 1, which is 1, over g of 1, which is 2, squared. And then it's just a matter of figuring out what that actually equals then. This ends up giving me 6/4, which I can give as a final answer either of 3/2, 1.5, or 1.5, depending on your personal preference there. Yeah, I'm saying difference quotient. Sorry, it's a bad habit because we were doing it for so long. Quotient rule. Thank you. So now we get to get into the normal line and tangent line equations and all that stuff that we were doing. So in this case, I'd like you to please write the equation of the normal line. Check your notes if you don't remember what the normal line means. To this point on this equation. It's going to give us a little practice with the derivatives of square roots as well along the way, which I think is a good thing for us. So you hopefully have now figured out and remembered that normal line is that line that's perpendicular to the tangent line. So in order to do this problem, you need to start by finding the tangent line slope. And of course, tangent line slope, that tells me you find the derivative. And in order to find that derivative, write your square root of x as x to the power of 1/2. All right, so when we use power rule here for y prime, our derivative, we should find that that equals 1 minus 1/2 x to the negative 1/2. Now, that's fine as an equation, but the next step that we have to do here is we have to take our x value and plug that in for x. Well, a lot of us are going to have trouble figuring out what x to the negative 1/2 is if we don't change the look of it. So I'm going to change that back into the way that we're used to seeing it. So the 1/2, I got a fraction in there, 1/2. And then the x to the power of negative 1/2, the negative in the exponent tells me that this x is in the bottom of my fraction. And x to the 1/2, again, is square root of x. It's a lot easier from that format now to think about plugging the 1 in for x and see what that's really going to give us. So I'm going to go ahead and plug in that 1 for x now. So y prime equals 1 minus 1/2 times the square root of 1. So that's going to end up being 1 minus a half, and 1 minus a half is 1/2. All right, now remember what we found here? We found in this 1/2 that that's the slope of the tangent line, because that was the derivative. We aren't interested in just using the slope of the tangent line, though. We are finding that only so we can actually use it to find the slope of the normal line. So the slope of the normal line, remember the normal line is perpendicular to the tangent line, so the slope perpendicular to the line with a slope of 1/2 is a -2. Because remember, perpendicular lines have opposite reciprocal slopes. So that's what all that work was for. It was just so I could figure out that the slope of my normal line was going to be -2. And now that I know that the slope of the normal line is -2, I can go ahead and write the rest of the equation, because I know it's going to be y equals -2x plus b. Now I just need to figure out what b is. Okay, when you do that work, you plug in our point that we're actually working with here for x and y. Solve for b, we find that b is 2, therefore your final answer, your equation, is y equals -2x plus 2. So a little bit more practice with these ideas. Let's find the equation of the tangent line this time of this equation. All right, and if we're looking for the equation of the tangent line, that means you need to find derivative. And if you need to find derivative of this particular equation, what rule are you going to use? Quotient rule. Yep, absolutely. So use quotient rule in order to find that derivative. And remember, once you find the derivative, actually plug in the point that we're working with here. Plug the 1 in for x. All right, so when you plug this into the quotient rule, this is what you're looking at. Now, of course, right now this just looks like a big, scary, ugly thing. But let's actually plug in our x value that we're working with here. An x value of 1 is going to make things a lot simpler to work with here. So the derivative at 1 is going to be 1 times e to the 1, and so on. E to the 1 times 1. Oops. It's all going to be over 1 squared. Notice what that gives us, though. It gives us e minus e on the top and a 1 on the bottom. Well, that's 0 over 1, and 0 over 1 equals 0. So the equation of the tangent line. Notice that it's tangent line here, so the slope that I just found is actually the slope that I want. No opposite reciprocals here, because that would be for normal line. The derivative actually gives us the tangent slope. And so now that I know this, I can go ahead and write the equation of the line. There's actually a really fast way to get to it at this point. But if you don't remember that fast way, of course, you could go ahead and write it out the long way. Y equals 0x plus b. And plug in our coordinates for our point and figure out what b is. And you should find that b equals e. So b equals that constant value e that was in there from the start. Now, I said there was an easier way that you might have been able to get this equation. Well, if the slope is 0, that means it's a horizontal line, and the horizontal line is always going to be y equals a constant. So it's just y equals e, which is the same thing it gives us if we do it the long way. Because we don't need to write the 0x, obviously.